Hi everyone, I'm Aditya from Stanford, and today I'm going to talk about Node2Vec, which is a new framework that we proposed for feature learning in networks, and this is joint work with Yuri Leskovich. Many interesting problems on networks can be cast in the framework of machine learning, and in many of these problems, what we are given is a network where some information is given to us about certain objects such as nodes. So for instance, in this network, we are given the colors of few nodes, and we're asked to predict the colors of the nodes for which we do not have such information. We can exploit the structural properties of this network to infer the colors of the remaining nodes. So this, as well as many other interesting machine learning problems such as link predictions, have a very general framework in which you take a network, build a model using some training data, and do some predictions. However, in going from a network to a model, there is this essential bottleneck that we need to resolve. And this bottleneck is that we cannot directly take a network's raw representation and use it to build a model. So this essential problem of constructing features from a network is what we are trying to solve. So given a network, for every node, we want a representation of its features, which can be then used to train a model. There's a lot of prior work in this field. So earliest research in machine learning in networks focused on manually curating features. So they designed a lot of features based on the structural properties of networks, such as the degree, the page rank, and used them for prediction. The most dominant paradigm in learning representations for networks is based on matrix factorization. These approaches enjoy a good theoretical backing, but empirically they do not scale well to real-world networks. Finally, in recent times, we have been seeing a lot of deep learning inspired approaches. They do very well in terms of their predictive power on networks, but often have the limitation that the training time for these approaches is exorbitantly high. So our motivation is that we need efficient, task-independent feature learning algorithms for machine learning in networks. So given any network which has lots of these nodes, we want to learn this mapping F that maps any node, say U, to a vector in d-dimensional subspace. So this mapping function F will give us features for any node in the network, which then can be used to train a model. So throughout my talk, I'll be using these words very interchangeably for the vector representation that we learn: features, embedding. They're all referring to a d-dimensional subspace in which we are projecting our nodes. The overview of our algorithmic framework is as follows. We have a goal in mind, and the goal that we have in mind is that we want to embed nodes with similar network neighborhoods close in the feature space. To achieve this goal, we will use the classic principle of maximum likelihood optimization. And one key observation that we make in optimizing this objective function that I'll propose shortly is that the notion of network neighborhoods should not be restrictive. By having a flexible notion of network neighborhoods, which is not tied to certain one-hop or two-hop distances or first-order, second-order proximity, these kind of notions, we can discover rich features for nodes U. So these network neighborhoods, as we call them, will be denoted by NS of U. Now this subscript S is what induces flexibility in defining these network neighborhoods. And this flexibility comes about through a generative process that we define based on biased second-order random walk procedures S. So this is the overall Node2Vec framework that I'm now going to describe in detail, starting with the goal for the optimization problem in this work. So the objective of Node2Vec, as we saw, is to learn a mapping that takes nodes in their raw representation and maps them to a d-dimensional continuous space of features. The specific objective that we're optimizing is that we want to maximize the log probability, which is conditional in nature. So the conditional comes from the fact that we want to predict feature representations which tell us about the neighborhood of a particular node U. So given any node U, we apply this projection operator that takes it to a low dimensional space, and the good mappings will be more predictive of its neighborhood. To make this objective more formal, we make some assumptions which get it tractability for the optimization algorithm that we use subsequently. So the one assumption that we make is that the conditional likelihood factorizes. So given any node u, it predicts each of its neighbors independently. So if we apply this assumption to our objective, we get a simplification that makes this objective very much tractable. Finally, we just now need to characterize the conditional likelihood for each of these individual terms where we are predicting these neighbors ni for every node u. And we do this through the softmax parametrization. So the softmax parametrization requires just one parameter. And in this case, it makes perfect sense to use the angle between the two vectors that we are trying to compare of how similar the feature vector representations are. So given this assumption of conditional likelihood being a factorial over the neighbors and the softmax parametrization, we can specify this optimization and use an SGD-based solver which will optimize it in very quick time. One missing component that remains in this objective, which has not been specified so far, is what is this neighborhood set of u. And I promised that we're going to define a flexible notion of network neighborhood. So before I tell you how we do that, let's see why it is important to have this flexible notion of a network neighborhood. So given this toy network, you have this node u, and we want to, let's say, get three neighbors which are most predictive about u. So a first-hand guess might want to take the three closest neighbors. So you take any of S1, S2, S3, 4, and take three of these and say that these are the neighbors which are most predictive about you. This indeed is intuitive, but it also has a limitation. The limitation is that this strategy, which resembles breadth-first search behavior, gives us only a local microscopic view of our neighborhood. And this might be restrictive when we are trying to learn representations which capture equivalences that extend far beyond our local neighborhood. The other extreme is when we go into the depth-first strategy, where we say that we want to sample neighbors which are strictly at increasing distances from the source. So this indeed provides us a global macroscopic view, but the disadvantage again turns out that if we go too far out, then we might not be really representative of the original source. So it would be nice if we had a way in which we could interpolate between these two extreme paradigms of restricting ourselves to just local neighborhoods as in BFS and to very high global neighborhoods as we do in DFS. So this is the next question that we try to answer, that how can we do this kind of interpolation which would make our embeddings much more representative of different equivalences. We do this by defining a generative process based on biased second-order random walks. So again, we are at this node u, and we want to pick up neighbors. So we do this by defining random walks starting at u. So let's say without loss of generality, we go to this node S4, and at S4 now we need to make a choice of which should be the second neighbor of u that we should be sampling. So because it's a random walk procedure, there are only restricted number of neighbors that we can sample from S4. So one option is that we go back to u. So in this case, the node is preferring, the random walk is preferring breadth-first search-like behavior because it wants to stay itself close to the source. So we assign this some unnormalized probability, let's say 1 by p. The other option is to go the DFS way, where we say that we go to a neighbor which is not connected with the source at all. So we go to S5, and again we can assign it some unnormalized probability, let's say 1 over q. And now the one case which is remaining, which is somewhere midway between BFS and DFS, and as we shall see, this is also indeed important because it truly provides us a smooth interpolation, is when we sample a neighbor which is connected to our original source. So in this case, from S4, we could go to S1. And because all the probabilities of the three cases should sum to 1, we do not need any additional parameter, and we can just say that this has an unnormalized probability of 1. So after normalization, all these will become valid probabilities. So to quickly summarize, how does this provide us this interpolation scheme? So if we have a low value of p, we are more likely to go back to our source, and this resembles BFS-like behavior. If we have a low value of q, we would prefer to go to a DFS-like behavior. One important question is, how do we learn these values of p and q? So they could be made part of our objective, and we could be optimizing over them as well. This, however, makes the optimization problem a bit harder And so what we do in our experiments is that we learn them in a semi-supervised fashion where we see a bit of the test data and set the values of P and Q appropriately. So in conclusion, this is how the node-to-vec algorithm looks like. So we start by computing the transition probabilities for our random walks, and this depends on the neighborhood strategy which is best for the network. So the values of P and Q which provide us the best transition probabilities, we compute these probabilities. The second step is now we actually simulate these random walks based on the previously computed probabilities. And then there are some design parameters which you can set based on your computation available, how many random walks you should do, what should be the length of a random walk, and so on and forth. Finally, once now, after we have sampled the network neighborhoods, we have our objective completely specified, and we can optimize it using stochastic gradient descent. So if you see each of these three steps, we see that this is an iterative procedure, and this procedure has a linear time complexity. And indeed, if you want to learn representations for each of these nodes, this is the best you can do in big O complexity. All the three individual phrases that I described are parallelizable, so this lends our algorithm additional scalability. Coming on to the experiments for node-to-vec, we conducted experiments which told us about different aspects of our algorithm. So the first aspect of our algorithm, which was also the motivation behind this work, is how well it does on classification and other machine learning tasks. So here I'm discussing the problem of multi-label classification. In this problem, we are given a network where we are shown the labels for few nodes. These labels can be more than one in numbers, which makes this problem even harder than the binary classification originally. And we test it on 3 data sets. Because of the general purpose nature of node-to-vec, the data sets that we pick are from very different domains. So we have a block catalog network where the bloggers are the nodes and the edges indicate follow relationships. The labels are the interests of the bloggers. We also experiment with a network from systems biology, which is the protein-protein interaction network for human beings. In this case, the labels correspond to the functions that the proteins play within the human body. The final network that we experiment with is a language network. So here the nodes represent the individual words and the edges indicate co-occurrences. And the labels correspond to the part of speech tags for each of these words. So for these 3 data sets, we compare our algorithm with a lot of benchmarks which have been shown to perform extremely well recent times. The first is spectral clustering, which is the primary algorithm that comes from the matrix factorization literature. The second is DeepWalk. So DeepWalk has an objective which is very similar to ours. However, it has no flexibility in exploring neighborhoods, so it proposes uniform random walks. Then the third one is Line, which has a very rigid strategy again in exploring neighborhoods. So it restricts itself to sampling only 1-hop and 2-hop neighborhoods. Even going beyond the predictive power on this multi-label classification, I'm also going to discuss experiments which test the robustness of node-to-vec to perturbations and scalability. So coming on to the results for the multi-label classification problem. So this table shows the results for a balanced split between the train and test sets. You can refer to more extensive experiments in the paper. But as we can see from this table that node-to-vec can achieve drastic gains over the competing methods. The closest method that comes to node-to-vec is DeepWalk. And even on DeepWalk, just by having an intelligent exploration strategy where we explore diverse neighborhoods, we can gain up to 22% without any additional time complexity. So, and as far as the other methods are concerned, spectral clustering, even though it enjoys a good theoretical backing, we see that it's extremely weak in practice. And Line, because it's of a restrictive neighborhood definition to 1- and 2-hop neighborhoods, is also not able to do well on this task. And the values of P and Q, which were used to get these results, show that it is important to have a flexible notion of a network neighborhood for sampling nodes. The second experiment is about how robust is our algorithm to noise a network structure. So we know that the real world networks are not perfect, There could be noise in the form of missing edges, where we have incomplete information, such as in biological networks. And there could also be noise in the form of false edges, so this is very common in sensor networks. So in both these cases, we see that the performance of Node2Vec degrades as we expect, but the degradation is very gradual. So if the missing edges are missing as high up to 50%, we just see that the macro F1 score degrades by 20%. And similarly, if the additional edges in the form of noisy edges is, let's say, 50% again, the degradation is not too high. The last aspect of algorithm, which really makes this method much more superior to the recent deep learning based approaches that have been coming up, which take a lot of time to train, is the scalability. So as we can see in this log-log plot between the time taken for learning these embeddings compared to the size of the network, we see that this algorithm scales linearly with the number of nodes in the network, and the constants that appear are pretty low. So for 1 million nodes, we take only 4 hours to learn the embeddings, and this is much, much better than the deep learning approaches, which take up to a week to just train networks. And I should add a caveat that in this case, we were doing the sampling using Python, and if we can do it using a much more optimized language, then we can also get much more higher improvements in terms of the time it takes to learn these embeddings. In conclusion, we have proposed Node2Vec, which is a general purpose framework for feature learning in networks. The key features of our framework are that we propose a locality preserving objective, which is very different from the ones proposed in the matrix factorization literature. In order to optimize this objective, we first have a prerequisite in the form of specifying a generative process over a graph. To achieve this goal, we define a family of biased random walks, and we show that this bias in random walks is important if we really have to capture the diversity in network patterns that could arise. Our algorithm is scalable and also robust to different kinds of perturbations. As a future extension of this work, it's also helpful if we can extend the random walk strategies to networks with specific structure, such as heterogeneous networks and sign networks, where we have additional information that can be used to bias our walks in even better ways. So thank you all for listening. All our code and data sets are available at this URL. Right now, we just have a basic Python implementation, but the C++ version should be coming out soon.
How did you decide on R, the number of walks, and L, the number of steps, and what sort of order of magnitude compared to the number of nodes?
So R and L are design parameters, and we used what has been done in prior work. So to give you some idea about the typical values that we used. So for networks with 100,000 nodes, we were using R to be just about 10 or 20, whereas the length of walks is also 40, 50. So these are really very small constants, which do not really contribute to the overall complexity of the algorithm by a significant amount. So we have experiments in the paper which show the effect of tuning these parameters. So as you would expect that if we have more number of walks, we're able to get more neighborhoods for the nodes, and this indeed gives us better representations. But the gain gradually levels off as we increase them beyond a certain value.
So in your examples, most of the networks, they have, say, up to a few millions of nodes, right? So, but what if you have a network that consists of a bit more than 1 billion nodes, and each node will have a vector of, say, 100 dimension, then this won't easily fit into the driver's memory, right? If you're running a Spark or anything. So how do you propose to go around this problem, handling the large number of vertices?
So I think this is the best option we have in terms of scalability. So we are not adding any time complexity. So as we saw that from our experiments, the complexity is linear in the size of the network with very little constants. So even if you have networks with 1 billion nodes, it will indeed become challenging from both a systems perspective and the algorithmic optimization happening underneath. But that's all I can say, that it should not, the performance should still be state of the art with respect to the other methods that we have available.
So just was wondering if you've done a little bit of research into how this might, how you might be able to use this on sort of a growing graph. So like, could you update a graph embedding over time as you see the edges coming in?
That's a very good question, and something which we are thinking about a future work, that you have a lot of cases where your networks are dynamic and you do not want to learn embeddings each time there is any minute change in the network. So one idea that we have been thinking about is that what if we can characterize what has been the modification in a network. So we do random walks within a local neighborhood around the modification. And this we think might be helpful to counter this problem.
Thank you.
Hi, thank you for the nice talk. And then I have a question about the P and Q values.
Right.
Actually, one thing I cannot easily get is the assumption that there is some optimal P and Q value when you run the random walk. So I'm just wondering, what if, for example, if you have multiple instances for the different P and Q values, and if you then for each configuration you can get each representation, then I'm wondering how it represents better or worse when you concatenate the representation. And the second kind of configuration is if you use some random fashion way of P and Q value, for example, given some prior, and then when you use a P and Q value based on some prior, then how that affect the algorithm?
If I understand your question correctly, so your question is mainly targeting the point that how do we get P and Q, and what values of P and Q should work well for networks.
So no, my question is about what if we use the multiple P and Q values and then concatenate the representation from each P and Q value? That was my first question. Would that help the representation or not? And the second question is, so right now we fix the P and Q value, assuming the P and Q value have optimal point. But what if we use some randomized value for P and Q based on some higher prior?
Okay. I can't give a definite answer to the impact on performance, but it might help indeed, because now we are going to explicitly sample different neighborhoods based on P and Q. But how many values of P and Q should we experiment with? And if we don't want to concatenate and make a very lengthy representation, because this is a dimensionality reduction technique in effect. So if all these questions can be figured out, then indeed it might be helpful to look at what you're suggesting.
Okay, thanks.
My question is related. I mean, you said it's not a good idea to optimize for P and Q, but if you did optimize for P and Q, does it characterize something about the network?
That's a good question. So in our paper, we give some hypotheses about what P and Q could lead on to in terms of interpretability. So there are notions of network equivalences that we have come from a lot of literature in sociology and various other fields, which tell about different kinds of equivalence. So you have equivalences based on homophily, where you have nodes close by being similar to one another. And then you have these notions of structural equivalence, where nodes could be not connected, they could be far off in the network, but they're playing similar roles. So P and Q, setting them to different values, could result in equivalences that correspond to different notions of network equivalence. Okay.
So thank you for a clear talk and also for making the code available. Two quick questions, actually. So the first one is, just to clarify, when you learn P and Q, do you do this online, like in a maximum likelihood type 2, or do you do cross-validation? I didn't quite follow your procedure.
We do the latter. So we train on 10% of the total data that we have. So what we're saying is that P and Q, even if you can do it in like a semi-supervised fashion with very little training data, And then when you're finally doing the predictions, you use whatever train test split you want to use. Even in those cases, our performance would be very state-of-the-art compared to the remaining methods.
I see. And the other thing is you do have a density model that you're estimating. So yours would be more like a variational autoencoder where you could actually detect the probability that a graph doesn't fit with a population of graphs. So you could do anomaly detection and security and so on. Have you explored those ideas?
Anomaly detection is a very interesting application where we think this framework could be extended. But to directly answer your question, we haven't done it so far, but it's an interesting direction for future work. Thank you.